All right, hello everybody. Good morning. Welcome back. Hope you all had a good break. Some announcements. Don't forget that the next sheet, so chapter 8, part 1, is at the end of the day tomorrow. It's due tomorrow because it covers some of the content from the recorded lecture. I just checked and I have 78 views and I have 90 students in 1070. So if you haven't watched the recorded lecture, then you are behind. Make sure you're watching that. There's 2 announcements about it on Blackboard. Both were sent as emails as well. So the next Achieve will be due next Monday. So that will be the second half of chapter 8 and the beginning of chapter 9, which we'll get to this week. Yeah.
The last Achieve, it was dated for like 9 p.m. instead of 9 a.m.
Okay.
So it was like
The one that's due this week?
no, the last one.
Okay, that's fine. That was an accident on my part, but as long as it's later, not an earlier due date, right? It was like Monday, but later. So Sunday night?
It was Sunday night.
Okay, I'll look into that then. Thank you. My office hour today is at 1. On Wednesday, my office hour is at 2. We all ready? Ready to focus, everybody? All right. So in that video, we talked about quantum numbers for electrons. So a lot of what happens in chemistry is focused on electrons within an atom but sharing between atoms. And so quantum numbers can describe an electron in an atom. So that's part of an atom. There are 4 quantum numbers. Each of these describe something different about where an electron is in an atom. So remember, an orbital is an area of space where an electron can exist. And these quantum numbers tell us about the orbitals and the spin of the electrons. So the first is the principal quantum number, or n. In this gives us information about the size of an orbital. The lowest possible n value is 1, and then we have integers, so 1, 2, 3, 4, 5, etc. So this tells us the size of the orbital, so lower principal quantum number means smaller orbital, and the energy. Smaller orbital means the electron's closer to the nucleus. That means that electron has a lower energy. L, which is our secondary quantum number, gives us information about the shape of the orbital. That also tells us information about energy. So L, that is, if an L is equal to 0, that is an s orbital, which is a spherical shape. If L is 1, that is a p orbital, which is a dumbbell shape. If it's 2, it's a d orbital, which is a 4-leaf clover shape, or a dumbbell with a ring. And then 3 is an f orbital. We're not going to talk about the shapes of f orbitals. It gets more complicated than we need to in Gen Chem 1. You might remember that p orbitals, here's an example of a p orbital, has a lobed shape that can exist in 3D space on any of the 3 axes. So in a p shell, we have a px orbital, py orbital, and pz. And so the magnetic quantum number tells us the orientation. So for a p orbital, we have 3 possible magnetic numbers. We won't be aligning a value for ml with a specific orientation. We just need to know the possible numbers for ml. And then spin ms, that fourth number just tells us if the electron in an orbital is spin up or spin down. In any individual orbital, that orbital can only hold 2 electrons, and those 2 electrons cannot have the same same set of quantum numbers, so all 4 quantum numbers. So if you have 2 electrons occupying the same orbital, they will have the same n, the same l, the same ml, but the ms value will be different. One will be plus 1/2, one will be minus 1/2. Let's see. Okay, we'll just talk through this example here, and then we'll go to new content. So this last learning check was providing 2 examples of sets of quantum numbers. That means we'll have 4 quantum numbers for a complete set for an electron in a 4D orbital. Knowing that it is a 4D orbital already locks us in with a value for n and a value for L. 4, the 4 part of 4D means principal quantum number 4. So we're at energy level 4. That means n is equal to 4. For any electron in the 4D orbital, n is equal to 4. Because it's a d orbital, that means that L must equal to 2. So any electron in a d orbital has an L value, secondary quantum number, equal to 2. And then ML, here's where we have some options. So ML, our restriction for ML is that it can be any value, any integer from negative L, so negative 2, to positive L, so positive 2. So ML can be negative 2, negative 1, 0, positive 1, or positive 2. You can select any ML value for an electron in a 4D orbital. It does not matter. I selected negative 1. And the last quantum number is our spin quantum number. MS can only ever equal plus 1/2 or minus 1/2. Because I'm writing 2 different sets of quantum numbers and I have the same NL and ML value, I made sure that the 2 MS values were different. One's plus 1/2, one's minus 1/2, because 2 electrons in the same atom cannot have the same set of all 4 quantum numbers. So they have to differ some way. And if we're talking about electrons in the 4D orbital, that can be by the MS value or by the ML value. Okay, questions on this? Questions on what was in the video? Anything you'd like me to review? All right, then we will go on to our next section. So we're going to kind of take quantum number sets and simplify it when we're talking about atoms that have a lot of electrons. So we can talk about, or not talk about, well, we can describe the electrons in an atom with quantum numbers. But remember, each electron has 4 quantum numbers. We have an atom that has 20 electrons. Each of the 20 electrons has its own set of 4 quantum numbers. That's a lot of quantum numbers to be writing out. That is a way to describe all of that. Let me write in some of these blanks here. Oh. Do you all have blanks on this slide? Oh, okay. Never mind. We're good then. Okay, so we can write a set of 4 quantum numbers for every electron, or we can simplify that by writing shorthand electron configurations. With this shorthand electron configurations, quantum numbers can be inferred. So for a hydrogen, it has 1 electron. It's in the lowest energy orbital. It has the lowest principal quantum number at 1. That means its L value must be 0. So that implies we have an s orbital, and we only have 1 electron. So we have 1 for the principal quantum number, s for L, which is our orbital shape, and then 1 because that's the number of electrons there. For oxygen, it has 6 electrons. So the first quantum number is 1 that can only have an L of 0, which is an s orbital, and each orbital can hold 2 electrons, so there's 2 electrons in that orbital. And if we increase in principal quantum number to 2, we can have an s orbital and a p orbital, 2 electrons in the s, and we can have up to 6 in the p orbital because there are 3 suborbitals for a p shell. But oxygen only has a total of 8 electrons, so 4 in the p shell. So we'll do a lot of electron configuration practice. We can also represent orbital energy by showing an orbital diagram. And these are really simplified. We'll see a more complicated one, which will help this look more, or just make more sense when we have more going on. But what we do for the orbital diagram is we draw a line for each individual orbital, and then we place an arrow to represent an electron in that orbital. These are represented on an energy scale, so we would have energy as a y-axis. 1s orbital is closest to the nucleus, that's lowest energy. 2s orbital is a little bit higher energy, so that would be higher on the energy scale. So this periodic table is not in your slides, but you might open up a periodic table to draw on it, or maybe do that after class. But when we're writing an electron configuration, looking at a specific atom and determining where those electrons are and in which orbitals in the atom, we can use a periodic table to determine where they are. So principal quantum number aligns with all of the periods, or the rows, in the periodic table. So principal quantum number 1 aligns with our first row, 2 for the second row, and so on. We think about hydrogen. Hydrogen has 1 electron in the lowest energy orbital. That's the 1s orbital. The first 2 columns here represent electrons in the s orbital, and helium. So helium has 2 electrons. They're both occupying the 1s orbital. The area with transition metals. So this lower area here represents electrons in the d orbital. And then the 6 columns on the right represent electrons in the p, except for helium. And then we have F and G for the lanthanide and actinide. So we said on the previous slide, oxygen's electron configuration is 1s2, 2s2, 2p4. Now we'll use the periodic table to see how that aligns with the placement of oxygen. So oxygen is here, element 8. If we start at the top left corner of the periodic table, principal quantum number 1, we have to work all the way through that row before we can get to oxygen. So that means its 1s shell is full with 2 electrons. Then we go to the second row. The 2s shell, which is represented with these atoms, lithium and beryllium, we also pass that before getting to oxygen. So that means the 2s shell is full. And then we're in the 2p shell. We're 4 atoms over, so we have 4 electrons in the 2p shell. Let's also do the electron configuration for lithium. So we have 3 electrons. We can write 3 possible configurations, but we typically provide the configuration for the highest energy electron. So if you're doing quantum numbers, we look at where lithium is. I'm going to go back to the periodic table. Lithium is element 3. So this means it has a full 1s shell and 1 electron in the 2s shell. So if we're providing quantum numbers, we'd provide the quantum numbers for the highest energy electron. Principal quantum number 2 for second row, second energy level. L is 0 because we have an s shell. That means ml must be 0. And then our spin can be plus 1/2 or minus 1/2. So that's with quantum numbers. We're writing out electron configurations. We have 1s2 because the 1s shell is full, and 2s1, we have 1 electron in the 2s shell. And then for the orbital diagram, here we have 2 orbitals, so they're arranged on an energy scale, just relative energy. The 1s shell is closer to the nucleus, it's lower energy than the 2s, so we put it lower on this y-axis for energy. We have 2 electrons in the 1s shell, so we draw one with spin up, one with spin down. We represent them with arrows. And then 2s shell has 1 electron. You can write that as the arrow pointing up for spin up or the arrow pointing down for spin down. Both are valid. Usually we'll draw spin up before we draw spin down. Oh, and this is for the last or highest energy electron. Yeah.
So does n equal 2 because it's in the second row?
Yes. Yeah. This next slide here has configurations for all elements in the second period. Now for the orbital diagram, this is not arranged on an energy scale. They're just all listed next to each other. If you were to arrange these on an energy scale, you have 1s below, 2s below, 2p. As you get further and further away from the nucleus, you have higher energy orbitals. So we just did lithium. Lithium has a full 1s shell, 1 electron in the 2s shell. Here's the electron configuration for lithium. If let's look at nitrogen. Going back to the periodic table, nitrogen is element 7. It has a full 1s shell, so that gives us 1s2. It has a full 2s shell, so we have 2s2, and then it has 3 electrons in the 2p shell. So 2 because we're in period 2, and p because it's on the right side of the periodic table. So if we look at the electron configuration here, we have full 1s shell, full 2s shell, and 3 electrons in the 2p shell. Orbital diagram, full 1s shell, full 2s shell, and then 3 electrons in the 2p. Now notice that these electrons are not paired up. That's intentional. So electrons repel each other. They're negatively charged, so they'll space out. They'll have as much space between them as possible. So if we have 3 electrons and we have 3 possible 2p orbitals, then we'll have 1 in each of those. So this would be like 2px, 2py, 2pz for the different orientations. And then when we get to oxygen, which has 1 additional electron, 2p4, then we pair them up. Let's also look at this last column here, so an abbreviated configuration. We can use noble gases to abbreviate electron configurations for core electrons. So if we look at, we'll keep talking about nitrogen. Notice there's helium in brackets and then 2s2, 2p3. If we go back to the periodic table, find nitrogen, element 7. You go up 1 row, so that brings us to row 1, and then all the way to the right for that noble gas. That noble gas is helium. So putting helium in brackets before the rest of the electron configuration implies that nitrogen has electrons, core electrons, that are the same as the electron configuration of helium. So I always go 1 row up and then all the way to the right to find that noble gas that can be used in brackets, and then the energy level that atom exists in, so nitrogen in energy level 2, principal quantum number 2, we write out all of those electrons. So we have helium in brackets, and then 2s2, 2p3. questions about electron configuration, orbital diagrams, abbreviations? All right, let's work on this learning check. So it's not an iClicker, the next one will be an iClicker. So we are constructing an energy level diagram. So that means we'll have energy level scale and writing the shorthand representation of ground state configuration of aluminum. So we got to find aluminum on the periodic table. I recommend starting with the electron configuration. So the 1s2, 2s2, etc. And then drawing them on an energy scale. As you go left to right in the electron configuration, you're increasing in energy. So lowest energy is 1s, then 2s, then 2p. And then provide one set of valid quantum numbers for the highest energy electron. So set of 4 quantum numbers that describe the highest energy electron here. I'll give you all some time to work on this before we go through it together. And if you want to have a quantum number that describes that.
So it goes all the way up to the maximum. Yeah, and then you go. So basically, basically you just fill up everything. So I wrote everything else. So you do the name of the thing. So what happens is that you always go like 1S, 2S, and 2P. So yes, like that. And then what
What is it?
Don't worry about it.
Oh, gosh. You have to do
I saw that. I was yeah. That's just a whole. Yeah.
We do, like, I feel like keeps us like.
All right, let's start going through this. So we're working with element aluminum. Aluminum is 13. Looking at the periodic table, I'll use a different color here. So I'll use green. Before we get to aluminum, so it has 13 electrons. It fills lowest energy shells first. The lowest energy shell, we can use the periodic table to find that. So lowest energy, we always start in the top left corner, helium. We go across the row. I'm sorry, hydrogen, we go across the row. So going across the first row, we have the 1s shell. We've not gotten to aluminum yet, so the 1s shell is full. Then we go to the next row. We first look at the 2s shell. So those two first elements represent 2s. We haven't gotten to aluminum yet, so the 2s shell is full. Now if we keep going across row 2, we get to the 2p shell. We've not hit aluminum yet, so the 2p shell is full. Then we go to row 3, 3s shell is full, and we continue across row 3, and we get to aluminum in the 3p shell, and it's the first element, so it has 1 electron in the 3p shell. So with all of that, we can write the electron configuration. So writing the full electron configuration, we'll talk about the abbreviation also. We have a full 1s shell, we have a full 2s shell, full 2p shell, 6 electrons are held in p orbitals, full 3s shell, so 2 electrons, and then 1 electron in the 3p shell. Questions on how I got that? I want to make sure everyone is good with electron configurations. Okay, well, to do the abbreviated electron configuration, we look 1 row above aluminum, so that's row 2, and then all the way at the end, we have neon. So we abbreviate by putting neon in brackets, and that takes care of everything through the second row. So that takes care of 1s2, 2s2, and 2p6. That's the electron configuration of neon, 1s2, 2s2, 2p6. So to continue and show the electron configuration of aluminum, then we write what's in the third row. So 3s2, 3p1. So that's the abbreviated version. now, we have the electron configuration. We can use that to write the orbital diagram. We start at the first 1s2. That will be our lowest energy orbital. It's closest to the nucleus, lowest energy. And we write this on an energy scale. So lowest energy is 1s. We have 1s orbital. Then we have 2s. And then we have 2p. Remember, p shells have 3 orbitals. So we write that as 3 separate lines. And I'm just writing the lines in to represent orbital energies. I'll add in electrons later. Then higher energy than 2p is the 3s. And then again, the 3p, which has 3 orbitals. So px, py, and pz, 3 orbitals in the p subshell. Based on the electron configuration, the 1s shell is full, so we can start filling in electrons. Remember, in a single orbital, only 1 electron can be spin up and 1 can be spin down. Often electrons are represented by an arrow with half of an arrowhead, so that's what I've drawn here. You can draw a full arrowhead either way, it's fine, but you'll probably see this a lot. So the 1s shell is full, the 2s shell is full. The 2p shell is full, so it's holding a total of 6 electrons. That's 2 per orbital. But I want to remind you that electrons will fill individual orbitals 1 electron per orbital before doubling up. So even though the 2p is full, I'm going to write in 1 electron in one of the 3, another electron, and another electron, each in its own individual orbitals, and then I'll double up. This is a good practice because if you don't have a full 2p orbital, I'm going to make sure you're not pairing up before you put 1 electron in each individual one. So 2p has 6, so we'll start pairing them up. 3s is full, and the 3p has 1 electron. Another important thing, I actually don't know if I already said this or not, but you must have in each orbital 1 electron spin up, so arrow pointing up, and 1 electron spin down, and arrow pointing down. If both of them are pointing up or both of them are pointing down, that's incorrect. That's implying that 2 electrons in the same orbital have the same 4 quantum numbers, and that is not allowed. So don't do that. 1 up and 1 down. Questions on orbital diagram? Okay, last part is providing 1 set of quantum numbers for the highest energy electron. What's the highest energy electron? The 3p1. So we've represented that on our orbital diagram. Higher energy as we go up, highest energy is in the 3p orbital. Also, higher quantum number, principal quantum number means higher energy. And p orbitals have higher energy than s orbitals. D orbitals generally have higher energy than p and s as well. So furthest away from the nucleus, highest energy electron. So we are writing a set of quantum numbers for this 3p1 electron here. So we will have an N, an L, an ML, and an MS. We have to have 4 quantum numbers to fully describe an electron. What's our N? 3. Yeah, it's in the 3rd energy level. It's a 3p electron, so that 3 means principal quantum number N is 3. What's our L? I heard 1 and I heard 2. So it's in the p orbital. P orbitals always have secondary quantum number L is equal to 1. S orbitals, L is equal to 0. D orbitals, L is equal to 2. So p orbitals, L is equal to 1. Let me go back to that slide from the video where I talked about secondary quantum numbers. if your L value is 0, then S orbital, L value 1, P orbital, D orbitals have L value 2, and so on. How about ML? -1, 0, 1. Any of those three is fine. So we won't be matching ML values, specific ML values with orientations. We don't know. We haven't specified if this is the 3P X, Y, or Z. So any of those three values are fine for ML. I will choose -1. And then MS? Plus or minus 1/2, you just have to pick one. I'm going to write plus 1/2 because we've drawn this electron and spin up. So that implies plus 1/2. If you wrote minus 1/2, that's also valid for that electron. That would be represented by the arrow pointing down in the orbital diagram. Okay. Yes.
And it just has an arrow up. Could it be arrow up or down? Does it matter?
Yes. It could be, no, it doesn't matter. Yeah, it could be up, it could be down. All right, let's continue on. So we have 2 more slides about that noble gas abbreviation that we can do. If you imagine writing an electron configuration for something like lead, all the way down here, that'd be a really long electron configuration. If you're starting with 1s2, 2s2, 2p6, 3s2, 3p6, etc., all the way down to energy level 6. So instead of writing all of that out, we're writing the electron configuration for lead. We can go up 1 row all the way to the right. That tells us xenon. If we write xenon in brackets, that represents what we call the core electrons for lead. And so that is, that xenon, we write that in brackets, that represents the electron configuration all the way up to 5p6. So 5p6 is the end of the electron configuration for xenon. So if we write that in brackets, we're representing up to 5p6. And then we would just continue with 6s2 and 6p. We'll talk about D's in a second. So going back to that slide, noble gas. Or the abbreviated or shorthand electron configurations can be used to make more compact electron configurations. So the core electrons are abbreviated by placing the noble gas immediately preceding the element of interest in brackets. So for aluminum, which we did, we use neon, which is in the row above aluminum and all the way to the right, that noble gas. The noble gas, or the electron configuration for neon is 1s2, 2s2, 2p6. So if you write neon in brackets, that's what it represents, the 1s2, 2s2, 2p6. And then we continue with the next row, 3s2 and 3p1, which is not represented by neon. Next slide has some more configurations for different elements. So for example, we talked about neon. If we look at argon, argon is at the end of the 3rd row. So that has the electron configuration of neon plus 3s2, 3p6. So if you have an element lower than argon, you can use argon in brackets. And that represents up to 3p6. And so on. So you can use krypton, xenon, etc. All right, another question here. We're going to determine the configuration of indium. Going back to the periodic table, indium is element 49. So you'll write the electron configuration. You can use the abbreviated. So first shorthand using the noble gas, and then also in the full form. And then construct an orbital diagram, but only, in this case, only use the electrons after the noble gas that you use in the abbreviation. One thing that we need to talk about before this is there's something a little bit special about the d orbitals. So if you follow the periodic table, which you can always do to write out electron configurations, the first row with d orbitals, so what looks like the 4d, is the 3d. So we decrease in principal quantum number by 1. You're going across a row and you're writing out the d orbital configuration. So if you're writing, let's see, titanium, element 22, its configuration using the abbreviation, we can use argon, which is the noble gas before titanium, and then 4s2, 3d2. So if you're writing out a d orbital, decrease in the principal quantum number. But the 3d orbital is still higher energy than the 4s. So you can follow this pattern. If you're drawing out the orbital diagram, 4s is lower energy than 3d. Just remember when you're writing it out that you decrease principal quantum number by 1, only for that d orbital. All right, let's start with this question here. Which one is, and not the whole thing, but part of it is an iClicker. So you're selecting the noble gas for indium and the correct abbreviated configuration for indium. And then continue working on the rest of the problem. But when you're doing the orbital diagram, you just not the four electrons. 1 minute, maybe. Yeah. All right, I'm going to close it in a few seconds. If you haven't, just make sure you submit. All right. All right, indium element 49. So if we're writing the shorthand version, go up a row all the way to the right, that's krypton, which will be in brackets. So krypton represents the electron configuration up to 4p6. So the next part of the electron configuration that we'll write is 5s2. Then we have 4d10. Do we decrease principal quantum number 1 by 1 for d orbitals? And then 5p1. So krypton in brackets. The 5s shell is full. The 4d shell is full. D shells can hold 10 electrons. And the 5p shell for indium has 1 electron in it. In the interest of time, I'm not going to write out the full electron configuration, but you would start with the 1s2, go all the way to 4p6, and then 5s2, 4d10, 5p1. For the energy, the orbital diagram, we'll start with what we call, these are valence electrons. So we'll talk more about what that word means, but essentially not the core electrons. So the valence electrons are what we'll represent on the energy diagram. So of these 3 orbitals, the 5s2, the 5s, is lower energy than the 4d. D orbitals, or D shells, have 5 orbitals. And then p's have 3. So orbital diagram on an energy scale just for the electrons after krypton. We have 5s, 4d, and 5p. These have 5 orbitals, p's have 3, s's have 1. The s shell is full, so we draw 1 electron spin up, 1 electron spin down. The d orbital is full, so I'm putting 1 in all 5 orbitals and then pairing up, making sure 1 electron is spin up, 1 electron is spin down for each orbital within the d shell. And then within the p shell, we have 1 electron there. That can be spin up or spin down. Questions? All right. Well, I have your assessment, so I'll pass this back to you now. So hang tight for a minute. Don't sound so upset.